Hi, and welcome to another interview with Yosis HQ. I'm Matt Venn, and with me I've got Andrew Zonenberg. So let's meet him now.
Hello.
So Andrew, could you, I'm just asking everybody this, could you just tell us your preferred pronouns?
He and him.
Okay. And from your Twitter bio, it looks like you're into a ton of different stuff like infosec, reverse engineering, high-speed digital. Like, if you could narrow it down to like just a couple of things, what would be your top few?
All of the above. I mean, really, a lot of my interests kind of tie together and overlap. I started getting into test equipment because I wanted to debug my open hardware networking projects. I started designing probes because all of the commercial active differential probes were too expensive. I started writing a scopeclient, which the back end of that is now the back end of glscopeclient. So libscope how, libscope protocols. The UI has been totally rewritten, but back in the day, scopeclient was the user interface for a JTAG-based logic analyzer that ran on Spartan 6 FPGAs during my thesis because Xilinx wouldn't give me chipscope for free, and I was on a grad student's budget. So one thing led to another, and here I am. But I mean, really, yeah, all these projects kind of tie into each other. You know, I'm using the probes with glscopeclient to debug hardware projects, and it's all just one big mesh of dependencies.
Where did your interest in hardware security come from? Was that like the beginning, or was it come from before?
So I'd been interested in security in general for a while. I had started to get, I was actually, so backing way up to when I was around 9 or 10, I started out tinkering in C. I found a C++ book on my dad's desk the summer before I turned 11 and started working my way through that. So I was software for a little while. Then shortly after that, I picked up a bunch of, I think, Forrest Mims books from Radio Shack and started working my way through those, building circuits back when Radio Shack was a thing, but also back when they actually sold hardware components. And so I started tinkering more on that, you know, building little op-amp circuits on a breadboard and stuff like that. And I quickly reached the limitations of what I could do with stuff at Radio Shack, and also, so I was limited in budget, being I think probably about a 13-year-old at the time with no job and no allowance or anything. So just, you know, whatever I could convince my dad to buy me from Radio Shack whenever we were in that area, which was limited. Also, obviously, I was limited by the component inventory at Radio Shack back in the early 2000s.
Have the catalog and kind of go through the catalog and circle the things you wanted most?
No, I was going through the books, and I would just go into Radio Shack and start picking stuff off the shelves, and hopefully I could find what I was looking for. Several projects got canceled because I just couldn't find the parts. I didn't know about DigiKey or anything back then. PCB fab was just not affordable for the average person back then. You know, this is probably 10 years before OshPark was a thing. So, I was pretty limited. I had, you know, some of the perf boards that I would play with, and I was actually wire wrapping because I didn't have a soldering iron at the time.
It seems like wire wrapping is a bit of a lost art, but the first.
I still have a wire wrapping tool, so I don't use it much anymore, but I still have it. I keep it around just in case I need it for something.
So then, more recently, you kind of moved from wrapping wires by hand to writing wires using, like, doing some RTL work and ASIC experience. I know that you can't say much about that, but one of the questions we had on Twitter was like, what, in your opinion, what's the big difference between FPGA and ASIC development?
So really the big difference is just the scale of testing and prototyping. With FPGA stuff, you can actually do full-scale testing of everything and deploy it as is, and if you have problems, okay, you go write some new code and you ship a new binary, problem solved. With ASIC, on the other hand, very often full-scale testing of the whole system in real time or near real time is just not possible. The best you can usually get is FPGA emulation, and bigger systems just won't fit in even a fairly large FPGA unless you go to Cadence or Synopsys or one of those other big players and buy some giant pile of FPGAs with some custom software that'll partition your designs between these multiple FPGAs and so on. And even then, you're going to be running it probably, I don't know, 1/10 real time, and so full real time testing is just not a thing. You have to do a lot more simulation, potentially multi-day or multi-week simulation. So yeah, I've only worked on one project of this sort, and it was a couple of years ago. So primarily, I do FPGA stuff.
Before you got on that, were you working with FPGAs? Like, did you get the experience to do an ASIC with FPGAs first?
Yeah, I've been doing FPGAs going back to actually predating my thesis. I think my first, so I was probably my second year of college. I was working on an operating system called PICNIX for PIC32s with my roommate. As you can tell from the name, it was a Unix-like platform. Didn't even really have any privilege separation or anything like that. We were just trying to get basic POSIX APIs to make writing firmware simpler. And we quickly ran into the limitations of, well, number one, I think 32 or 128K of RAM, and number two, just limitations on available resources, no MMU, fixed memory mapping, there was protection between user space and supervisor mode, but nothing beyond there. So I started looking around. I couldn't find any MIPS CPUs with a full MMU and external memory map available, and so I started building one. I got I think it was a little Spartan 3A that I think at the time I was basement etching boards in the electronics club at RPI. So started playing around with these were TQFP like Spartan 3A 50 100K gates. My first actual real FPGA project was a group on campus had asked me to go design for some robotics project. They asked me to design a servo motor controller that would do 32 channels of servo PWM off of a UART, and we couldn't find any microcontroller that had 32 PWM channels, so I had to go build one.
Classic FPGA application.
Yeah, so I did that in there's a Spartan 3A on an Express PCB board. Again, this predated batch fab really being a thing. So just, I think, 2 layers Express PCB, no DRC. I had to do bodges in the board because I missed a net in the schematic that the layout didn't have, and there was no way to tell that automatically. So, yeah, the tools were pretty limited at the time. I mean, I'm sure in that same year, if you wanted to go buy Altium or whatever, it would have been fine. But the tools available to the little guys were not really a thing. I think I may have discovered KiCad at that point, but not having access.
Is KiCad your go-to package at the moment?
Yeah, I've been using it for quite a few years now. I started as soon as I left Express PCB. I went to it, and I haven't gone back. Back in version 4, I actually did a lot of development work on blind via. All the blind via, micro via drill support is probably still my code because what was there was completely broken, and I had to redo it.
I think one of the first times I kind of became aware of the work that you're doing was finding your PCB checklist. You got like this Git repository. I'll link it in the video description, but that's so helpful to catch always the things that gets you when you're designing a PCB. Just have to go through that list and tick off all the boxes.
That checklist has saved me personally probably tens of thousands of dollars of respins and scrapped components and untold hundreds of hours of rework.
Yeah. So I know that when we were speaking earlier about the kind of topics we're going to talk about in the interview, one of the things that you said was that you're interested in advancing the state of the art in open hardware and software on the high speed or high performance end of things. So, like, has that come from, like, what's your motivation there? Like, is it that you want to see more open source or open hardware projects succeed with high speed stuff, or do you like think that open source tooling would be improved? Like, where's your motivation come from?
So it's a combination of everything. I started getting into this again because of networking. I was getting fed up with what I could get from eBay, Cisco switching, and random routers thrown together out of whatever Linux PC I built off parts on Newegg and so on. So I wanted to be able to build something a little bit more performant. Switch chipsets are basically not a thing if you're not Cisco or Avago or Cisco or Arista or one of the other big players. You either can't get them or you can't get data sheets. You gotta pay an arm and a leg and sign away your firstborn son to even get them to show you the NDA.
And just to be clear, when you're talking about switches, you're talking about network switches, right?
Correct.
Like gigabit fiber cable?
So 1 gig, you can Microchip, after they acquired Micro, does have a small handful of really small, basic 1 gig Ethernet switches. We're talking 4 or 5 ports. I think they have one that's 6 or 7. So, we're talking something on the scale like a Netgear GS108 or something like that. That is actually possible to build, as far as I know, with parts available from distributors in quantity 1, no NDAs in the data sheets. But if you want to start building anything on the higher end, that's just not really a thing. Like, one of my goals is to replace a bunch of the Cisco catalysts, 24 1 gig and 24 1 gig copper and 4 1 gig fiber uplink ports, and ideally I would like to have 10 gig uplinks. And so I have a bunch of these switches that I'd really like to replace with something open hardware. And again, this was also partially motivated by security concerns, because I can't afford to buy new Cisco switching on a one-person budget. And if I wanted to buy secondhand eBay switching like I've been doing, things are generally end of life or very close to it by the time they even show up in my lab, and I'm not thrilled about not getting security patches for any of my stuff. And really, my needs in software are not that complicated. I'm not doing complex multicast setups or anything. I just want lots of ports, lots of bandwidth, and basic VLANs and trunking. And so
to be able to trust it.
Exactly. And so designing a switch with that feature set is not that difficult, but it does require some higher performance debug capabilities. And so
that was the next thing I was going to ask, is like, where are the challenges in building a high-speed switch like that? The board layouts, the components?
It's a bit of everything. The RTL is actually comparatively easy if you're reasonably competent with FPGA stuff. The board design is more complex just because you've got such a large board. We're talking something, the full 19-inch rack enclosure in size. Then you've got at least 1 gigabit signals reaching fairly long distances, so you need to pay attention to loss and jitter and so on. And I wanted to make sure that this was going to work the first time, because we're talking a large, expensive board with a several $100 FPGA on it, and as a one-man shop, there is not going to be a respin of this board. I'm going to make however many I need. I'm going to populate at least one of them to start, and if it doesn't work, okay, I only wasted one board worth of parts, but the project's over. And if it does work, then I'll populate a few more. But that's really, a lot of this stuff was motivated by trying to make sure that I was going to get things right the first time, and that if there was a problem, that I would be able to repair and rework it.
Okay. So this is a really great example then. So you got something that's going to be complicated to make because of the constraints that you just said, and you want to be able to do it in one time, get it right first time, or if something goes wrong, then have the ability to debug it. So let's start with the first part of that. How do you make sure that it works first time? Simulation?
So obviously the PCB checklist is a big thing, and yeah, simulation is another one, as far as both the RTL design with something this complicated. The RTL design needs to be tested either on dev boards or simulation or a combination. Tested enough that you're at least confident, number one, your design will fit in the FPGA. So in this case, for example, I'm looking at using a Kintex 7, the 160K cell in the FFG 676 package. This was, I wanted to stick with Xilinx because that's what I have a lot of experience with, and this is literally the only choice in components, because this is about a $300 part. Anything smaller definitely won't fit. And anything bigger starts to get into 4-digit price tags. Either the, so the next Kintex 7 up doesn't work with a free tool chain, and compatibility with the free tooling was a critical design requirement, both so I don't have to shell out $3,000 on Vivado, and being an open hardware project, I want to try and keep the barrier to entry low as far as people working on it themselves. And so I wanted to limit myself to parts that were available in free Vivado. And so if I needed more capacity, that means jumping to UltraScale, which, again, is low 4-digit price tags, completely not footprint compatible, different core voltages that need a whole board respin. And so before I make this board, I have to be absolutely certain that I can fit everything I need in the 7K160. And if it doesn't fit, either cancel the project or cut features or something, because it'd be a complete board redesign and probably doubling in system costs to use a larger FPGA. So a lot of design there.
I know that you use a program called Sonnet to do some PCB simulation. Is that something that you would use to help you with this?
Absolutely. I would use that for all of my high-speed simulations. It's a great tool that is unfortunately not free. It's actually quite expensive. They no longer publish pricing, but they do have pricing available in the Internet Archive. If you search their product suites page and go back to about mid-2018, 2019, I don't think the prices have changed since then.
Well, we're talking killer dollars, though, aren't we?
Oh, as a minimum, yeah. Even their entry-level version, I think at the time was like $4,500 for the lowest level paid version. They have a free light version that's essentially useless. The version I'm using now is level 3 gold, which MSRP for that circa 2018 was on the order of 13,000, and I'm looking at upgrading to Pro, which is about double that as soon as I get budget, because even gold still limits you to 3 signal layers and 2 gigabytes of RAM. Right. I spent quite a while looking at the available open source options for EM simulation, OpenEMS, and so on, and the impression I got from them was that they're great solvers that have essentially no user interface. If you're okay with doing all of your design in Python scripts and spitting out XY coordinates and feeding it to the simulator and then writing some code to visualize the results and analyze it, they're probably okay. I know some people who have done some fairly impressive work with them. But for somebody like me who just wants to get a project done, it's not really an option. I mean, I'm definitely looking forward to them maturing to the point that I can use them for this sort of work. I think if somebody wants to put in the level of funding that KiCad's been getting, multiple full-time developers for several years, I think it's got potential. I mean, by the 2030s, there's a good chance that if we get that level of funding soon, that, again, OpenEMS or I think Elmer or some of the other tools in that class could potentially reach the level of maturity that they're useful for this sort of design by themselves. But as of right now, basically, I was actually trying to do real projects. I looked at what it would cost me in time and budget to convert OpenEMS into something I could use. I looked at the cost of a Sonnet seat, and it wasn't even close.
So would you say that that kind of stuff is like a requirement for doing high-speed design, or is it possible to build up an intuition and just be able to do a layout that you know is going to work?
So it depends a lot on exactly what you're doing and how tight your tolerances are. So in my case, for example, I was working on test equipment projects, probes, oscilloscopes, and things like that. And so if you're trying to accurately represent a signal, fractions of a dB in loss matter. Very flat frequency response matters. For pure digital stuff, if you just want something to work and be readable, you can get away with a lot more. That being said, there are definitely things that, like, for example, connectors like an SMA where it's got a big center pin that's going to lower the impedance. You're going to have all that extra metal there coupling to your ground plane. And so generally you will have to remove some metal under there. And I usually kind of guesstimate that I want to start with about the size of the pin as the cutout, but I do usually have to do a parameter sweep. And again, it depends on the stack up. And you can get an intuition for what roughly needs to be done. You can get close. Some of the closed form calculators like Saturn PCB and so on are decent for things like just calculating, okay, what width should my trace be for a 50 ohm trace? As you start to get to things like certainly double-digit gigabits, when you've got either coax connectors or just connectors in general are a pain because, again, you've got differences in traits with, the width is going to be wrong for 50 ohms, and you have to add either ground plane cutouts or move ground closer or further or something like that. And unfortunately, there is not any closed form way to approximate this, and you can gut check that a cutout is required, but trying to size it optimally is hard. The alternative is really just to do 10 boards with 10 different size cutouts and see which one works best. Throw them on a VNA and experiment. And there comes a point at which that costs more than simulating.
Yeah, that does take us. So maybe that takes us on to the next bit. So now you've got your boards and you want to actually characterize them. So you need like a VNA, you need a scope, you need the wires, you need the probes, and you need the software to understand what's going on. Mm-hmm. So, I mean, we can talk about all of that stuff really. So I know that you've just got a new addition to your lab in terms of on the scope side. Do you want to say something about that?
Yeah, that was a 16 gigahertz LaCroix SDA 816. I had been watching the high-end, I like LaCroix scopes, I've been using them for years, and so I wanted to stick with them. Also, LaCroix is kind of at least on the upper end, certainly into the gigahertz bandwidth class. LaCroix is kind of the tier 1 platform for a glscope client right now, in part because it's been my daily driver for so long. That driver is optimized inside out and backwards. I've spent a ton of time tuning it. Also, just LaCroix's Skippy stack is fairly efficient, and it handles things like multiple queued operations fairly well and things like that. That a lot of, for example, the Tech MS06 is a great scope if you're using it sitting at the front panel, but their software stack does not handle multiple concurrent operations really at all. It wants you to do one thing, get a response back. If you send a command while it's in the middle of something else, it'll just choke and potentially even lock up for a couple of seconds and drop commands during that time frame. It's just a general pain to work with.
So this is when you're driving a scope using like an interface from a computer?
Yes. And so I have not used any high-end modern Keysight stuff, so I can't comment on that. Also, Roden Schwartz. Pico has a really nice SDK for talking to their scopes. My main complaint there is that it is a proprietary API, and each scope family has a different, they're fairly orthogonal APIs in that the APIs for one scope are almost the same as the APIs for another, but they're not the same. So you do need to write different driver code to work with each of their device families and so on.
So I guess it's inevitable, isn't it?
Yeah, but on the other hand, in terms of waveforms per second, Pico blows away everything else I've used by probably close to an order of magnitude. I've got 1.52 gigabits a second of waveforms streaming off of Picoscope 6000 series, and my LaCroix on a good day will get 300 or 400 megabits per second of waveform data. And the next best actually was the Tech MS06, which was getting about 60, and then most other stuff is single digits to very low double digits that I've tested. And again, part of this is the glscope client drivers for these may not be the most optimized, but also there is massive differences in vendor Skippy stacks as far as how efficient they are. And a lot of these scopes were not really designed with headless operation in mind from the start, and it was meant for ATE operations where you're scripting configurations and then maybe grab one waveform for a pass-fail test. It was not meant for real-time streaming of waveforms and doing protocol decoding on a PC and so on. So a lot of these, nobody put in the effort to optimize their software for this use case.
Okay, so we've got like the scope in the middle. We can go either this way to the software side and talk about glscope client, or that way to how you actually connect it to the board and talk about the work that you've done with probes. Which one do you want to talk about first?
No preference. I mean, both of them are interesting to our audience.
Yeah, well, let's talk about the probes first then, because we got these PCBs back. Let's say we didn't have access to Sonnet. Although one thing that we'll come back to probably is just talk a bit about your kind of community efforts and your community work. But let's just say that you didn't know any nice person that would help you out with running a simulation on Sonnet. You've done like your 10 test ground cutouts, you've got your PCB back. Now you want to actually start measuring it. So what can you say about like your work with on the probe side of things? Because I've seen you do like two separate ones, like one, that kind of classic one where you don't have a ground clip on the probe, you have like the ground return right next to it, and then the other one which is actually like you solder it on to the PCB. I've never seen that before.
So I've actually got a pretty wide range of probes in development at various stages of maturity. So the AKL PT1s, just bang up a little bit, the naming convention is all anti-kernel labs, P is for passive, T is for transmission line, and then just a model number within there. So, for example, a differential probe or an active probe would be AKL AD something. So the PT1 is the handheld version. The Signal Path did a video on it if you want to link it. That was a pre-production kind of beta level unit. I'm still working on fine-tuning the frequency response. And yeah, as you mentioned, that one does have a ground needle right next to the tip. It does actually have, he didn't show it in the video, but there is a second ground position about a centimeter up and kind of diagonally aft on the shaft of the probe, but you can put a ground in. That one will actually rotate in the socket, so you can adjust spacing of the ground to the signal to probe test points at different distances from ground. You do get some additional inductance, so that is only good to 1 to 2 gigahertz, depending on which grounding mode you're using and so on, but it gives you a lot more convenience and flexibility, and so you can kind of trade between the two. I also supply a longer, flexible ground wire that you can use the same way you use a normal alligator clip ground, and again, that's even worse. It's only good to a couple hundred megahertz, but with transmission
and you're
line
selling
probe,
these out of your anti-kernel shop, right? I saw a few of them online the other day.
So they're actually sold through Elegant Invention. That's a friend of mine has a Shopify store set up, and so she's kind of my distributor for these. And they're all obviously open hardware. I'm just selling assembled units to fund further research and development on future stuff. Actually, I'm talking to somebody who's interested in doing some paid development on glscopeclient here and there, and so I've got about $800 in profit from sales of these probes so far that I'm probably going to try and plow into that, and if that works out, maybe I can have somebody put in a week every couple of months to paid development on it and see how that goes. So,
Nice. So then the other one is like it looked like a flex PCB that you solder directly to the circuit board.
So that's the AKL PT2. That is the first one that's actually available for sale right now. The PT1, I did a Kickstarter about just about a year ago now, and that was actually a mistake. The design was not nearly mature enough. It was about a 2.5 gigahertz probe at the time. The latest prototypes are in excess of 6, and I'm just trying to flatten out the frequency response more. So I will be offering assembled units for sale once I'm satisfied with the performance. And again, obviously, if somebody wants to pull the current design files off GitHub and make one, go for it, but just know it's going to get better.
And are they reusable after you've soldered them? Can you unsolder
Correct.
them?
It is designed to be reusable. I actually have not worn one out from soldering yet. I have some in my lab that I've used quite a few times in various projects, and I haven't worn one out yet. I've destroyed one so far when I had the tape that I had used to secure it slipped, and the solder joints at the tip are not designed to provide any mechanical support whatsoever. The castellations at the tip are tiny, and so you need to tape the thing to the board first, and once you're sure it's not going to move, then you solder it. And then in the reverse, when you're taking it off the board, desolder it first, and then once it's completely free, then remove the tape. And so as long as you do that, they'll last. I mean, again, I couldn't put a number on it because I haven't broken one yet from actual use. I've only ever damaged them from putting excessive force on them.
How many times have you unsoldered one so far?
I've got some that I've used 10 plus times. I mean, I've just got a bin of them sitting in the lab, and so I couldn't tell you how many times each one has been used. But yeah, okay. I know during testing and characterization, I've put 10 plus load cycles on many of them, and they look new, so.
Cool. Yosis HQ, open source EDA tools and related software development. Okay, so we've got another question from DSP8bit on Twitter that's related, and they're asking, what's the cheapest bit of equipment for signal integrity, and any recommendations for signal integrity beginners working with USB 3, DDR, DDR2 with FPGAs?
So the Short answer is, unfortunately, there's not anything good. Generally, you're going to need lots of bandwidth and lots of sample rate, and that doesn't come cheap. I am working in the very long term on some open hardware instrumentation, which will be... It's not going to be cheaper, probably, than the commercial alternatives. I mean, you'll get all the software packages free. You'll be able to write custom firmware for it and just have all the other advantages of open hardware. But the A to D converter for some of these higher-end scopes, I'm looking at one from Analog Devices that's 10 gigasamples per second, so I'd use that for about a 1 gigahertz bandwidth scope, or several of them interleaved for higher bandwidth. And the list price on DigiKey is about $3,500 for the A to D converter, plus the FPGA, plus probably dual-channel DDR4 to keep up with the 120 gigabits per second of waveform data coming off of it.
And you're not even talking about preamps or like signal conditioning.
That's not including any of the front end or anything. That's just for the A to D converter. And so you'd be looking at easily $5,000+ in parts per channel of the scope. And so something.
So maybe like a decent brand, but secondhand and like 4 or 5 years old. What would be your recommendation for somebody who did want to get into it?
4 to 5 years is still a little bit on the new side.
Okay.
It depends on how fast you're going. Roughly speaking, there's kind of 3 classes of test equipment out there. There's the current generation stuff, bought new from a dealer, fully supported, full warranty and everything. It's going to cost you an arm and a leg, and honestly, probably not worth buying unless you actually need bleeding edge performance or extreme size, density, power efficiency, and so on really matters to you. On the opposite extreme, there's what a lot of the smaller hobbyists and so on are using, which is go on eBay, find whatever you can, and it's probably going to be 20 plus years old. There's some really affordable scopes out there that were lab queens back in the day, and we're talking things that are running Windows 2000 or XP, Pentium 2 with VGA output on the back, and ancient dinosaurs by modern PC standards, but the analog stuff still works. I have a friend who got and again, I'm speaking mostly about LaCroix, not because they're better than the alternatives, just what I'm most familiar with. So don't take this as a recommendation of their products being better than the alternatives. That being said, they do make good stuff.
Yeah.
Okay. I have a friend who picked up one of their disk drive analyzers, the DDA 5000 series. She snagged it on eBay for, I want to say, somewhere in the $1,000 to $2,000 range for 4-channel, 5 gigahertz, 10 gigasample. And again, it was an ancient boat anchor running Windows 2000, but it still works, and she uses it for signal integrity stuff.
Yeah. Nice.
So, you can get some really nice deals if you're willing to go old. The downside is this is probably a decade out of support, and if it breaks, good luck getting spare parts for it. And then kind
Send
of in
it to the
between
signal
path. Yeah, even that, a lot of the things that are likely to break on these are, some ASIC finally gave up the ghost and, haven't been made in 10 years. The fab closed 5 years ago. So then kind of in between these, you get to the class that I primarily use in my own lab, which is what I'm going to call premium secondhand or manufacturer refurb, stuff like that. So these are scopes that are, for the most part, still in manufacturer support, but no longer being produced, or at least these are, say, retired sales demo units, or something a customer traded in to get the next model up, something like that. So in my lab right now, I've got a WaveRunner 8000 series that, with all the trade-ins and everything, I paid less than that, but the asking price from the manufacturer was about $20,000 US, and MSRP was around 40. Roughly speaking, stuff in this class, you're looking at paying about half a list price.
Right.
Then the other one I have is the SDA 816. That is actually an older model. It is out of support for the most part. It's a 2009 model year, and I bought it like a month ago, to give you an idea. That one cost me about $33,000, and list price for that was somewhere in the $100,000 to $250,000 range back in 2009. So the reason I was willing to consider a model that old is because it's close enough to the current generation SDA8ZIB series that LaCroix will upgrade it to the current model. It's not going to be cheap. It'll cost you about $40,000. I'm hoping to get that done next year. But at that point, it will be a currently supported model, and I'll be able to get spare parts for it and so on. And so I'm planning on keeping this scope out into the 2030s. And so getting that 7+ year extended support was kind of a critical requirement because, I spent more on this than my wife's car. So we need to make sure that this scope will outlive the car.
Okay, cool. So let's now progress to the other side. So talking about the software. So you've got your solder-on probes. They're going to your 30 grand oscilloscope, and now you want to be doing some signal integrity
work. on the scope side, so I have started some R&D projects that they've kind of been back burner for a while, in part because they were useless without good probes, and so at some point I may get back to it. So one thing that you can do to get fairly good high performance specifically eye patterns or like rising edge plots, something, as long as it's a repetitive signal. And for signal integrity, luckily, that's usually the case. If you're not doing protocol decodes and you only care about the shape of the edges, you can get away with a much cheaper option, which is a sampling scope. And so I actually built...
Yeah, so on the topic of sampling scopes, Ted Yapo did a really fantastic SuperCon talk. So if anyone's interested in finding out about sampling scopes, check that talk out.
Yeah, so I've actually been talking to him a lot, and I've got... one design that I prototyped already. It's a PMOD, about $50 bill of materials cost, that sends out a signal from the FPGA, runs it through a 2-port network of your choice, and then receives it back and digitizes it with, I think, 12-bit vertical resolution and 100 picosecond time resolution, so the equivalent of 10 gigasamples per second. So it's good out to, at least probably a gigahertz or so of bandwidth, although I never actually characterized the rise time on it. And so that was just a comparator and a DAC, basically, and all the other intelligence was in the FPGA. And so I have a next generation design that I started working on probably 2 years ago. I didn't have any EM simulation tool at the time, and so a lot of the layout is probably going to have to be redone once I've simulated it. I put it on ice in part because I didn't have any simulation tools, and also in part because at the time I hadn't really started the probe project, and therefore a fast scope without a good probe is useless. That project
actually is going to that back to that question from DSP 8-bit, then something like that could actually be quite a cheap way to characterize repetitive signals.
Yes, the only problem is there's not really a plug-and-play solution available to just buy or build right now. So that's kind of where I was getting to with this project called Freesample, which seems a perfect name for a free software sampling scope. There is a GitHub repo for it under my GitHub. However, it's kind of been abandoned for the last year and a half. Like I said, if you try to build it right now, the layout's not even done. So feel free to look at it, but don't try building it. Okay. And so this design used a TI deserializer to recover a clock from an incoming data stream, so you could do sampling on, say, an 8B10B stream or something like that. It also had a precision delay line, a TI PLL, and in theory should give you single picosecond horizontal resolution, and I believe 16-bit vertical. And again, there will be some noise and jitter, so some of that's going to be empty resolution, but I wanted to make sure that I was pushing it as far as I could, so I provided the capability. So the time base has a 25 picosecond delay in the PLL and a 3 picosecond delay, and you can beat them against each other to get 1 picosecond resolution in theory. Cool. And so that design, the front end was intended to have 10 gigahertz bandwidth, and so it's something you could use out to several gigabits per second data rates, and it would do clock recovery triggering and so on. So I never actually built it. Who knows if it'll work? The basic architecture is sound. I've prototyped it and proven it already. The idea is to use a cheap I2C DAC and a latching comparator to directly digitize the cumulative density, or the cumulative distribution function of a signal. So essentially what you're doing is at each point in time, at each voltage in your 2D eye pattern or density plot, you take a whole bunch of measurements at each point and these are 1-bit measurements off a comparator with the clock swept to the appropriate phase. And so that gives you 1 bit of voltage is greater than or less than this voltage at this time. And so by dividing that by the number of samples, you divide that by the number of samples to get the probability of the signal being less than that voltage. Then you scan over the whole XY pattern, and that gives you a direct statistical measure. You're directly measuring the probability, essentially, of the signal being less than that voltage. That gives you the CDF of the signal. Then you take the partial derivative in the vertical axis.
CDF, sorry, what's that?
Cumulative distribution function.
Okay.
So basically, probability of f of x is less than x, or f of t is less than x. And
but it's important to say that this is only good for repetitive signals, like a clock signal. And if you want to do protocol decoding, you have to do something completely different.
Correct. However, you can use it for signal integrity measurements on protocol data, or it doesn't. The signal itself does not have to be exactly repeating, because you're measuring the statistical properties of the signal. And so if sometimes it's 1 and sometimes it's 0, it's fine because you're going to see both of them reasonably often.
Okay.
Anyway, so yeah, you measure the CDF directly, you take the partial derivative in the vertical axis, that gives you the PDF, which is the probability of the voltage equaling a given value at a given time. And guess what? That's an I pattern.
Okay, right. Yeah.
So it's a very inexpensive way of getting this measurement compared to the classic sampling scopes use a sample and hold and a fast A to D and so on, and this design uses a comparator instead. So you don't actually even have an A to D converter in there. The downside of this architecture is you do have to take a lot more samples. You're looking at taking potentially thousands of samples per pixel. So with a full HD resolution I pattern, say, just for example, 720p would be roughly a 1.25 gigabit per second, so 800 picosecond UI, 1600 pixels wide by, say, 700-ish A to D values high. You're looking at about roughly a megapixel worth of data times many thousands of samples per pixel to get a nice smooth rendering. So you're looking at gigasamples of waveform data at, maybe a few kilohertz sampling rates. So you're looking at minutes to hours of acquisition time for one I pattern. But on the other hand, it's also, I'm targeting about a $1,000 bill of materials cost for a 10 gigahertz bandwidth scope. So these are the trade-offs you take.
Yeah. So let's finish up by talking about glscopeclient, because that's something that you've been doing a lot of work on recently, and you've got some videos on your channel about like showing off some demos. So is it what's it about? Because it seems like it's got a couple of uses, like at least for signal integrity, but also protocol decoding.
So the ultimate goal is to be a one-stop shop for analysis of time domain, or mostly time domain waveforms. It has some frequency domain capabilities. You can view FFTs and so on with it as well. But it's meant to be a one-stop shop for analysis of, I'll just say, waveform data in general, and also remote control of instruments. So either remote operation of a instrument that also has a front panel user interface, or full headless operation of something like Picoscope, or Digilant just sent me some of their analog discovery hardware that I'm going to be adding support for soon as well. So any of those headless instruments, and all of the open hardware scope projects that I'm working on are also going to be headless. They will be intended for glscopeclient to be the sole user interface. Or more precisely, libscopehal will be the sole API. glscopeclient is the supported interface, but there is a fairly clean front-end, back-end separation. The intent was to make automated testing, or potentially even a full custom third-party user interface, an option, talking directly to libscopehal and libscope protocols. Everything is permissively licensed. It's all 3-clause BSD. Interop with vendors was very much a goal. I would love if, for example, some of our protocol decodes ended up being shipped on scope firmware from a scope vendor, and we went with the permissive BSD license specifically to enable that. I would love if, especially some of the smaller scope vendors that are more weak in the software department, if they would just ship a Linux distro and a touchscreen optimized version of glscopeclient on the scope directly. That would be great. Who knows if that's actually going to happen, but at this point, I'm actually talking to 3 different instrument vendors. 2 of them have already sent hardware for testing. Pico and Digilant have both sent scopes over for testing. So I've got a Picoscope 6000. I've got the new Analog Discovery 3000, the older Analog Discovery and Digital Discovery. We've actually been talking to Siglent as well. They haven't sent over hardware because one of our contributors already has one, but they've given us a bunch of unlock codes for various software packages. They've enabled the MSO option, and they're looking at collaborating with us as far as getting access to additional hardware for testing and development. So a lot of the smaller instrument vendors are starting to realize the benefits of working with the community and having open source tooling available, because a lot of the capabilities that glscopeclient has, especially for more advanced signal processing, these are things these instrument vendors have wanted to have and didn't have the resources to develop in-house, and we've got open tools to do it already. And so, again, I'm not trying to necessarily kill proprietary scope firmware, but it would not be an undesirable side effect.
So what's the next couple of goals that you're working on with glscopeclient?
The kind of the roadmap right now, so far it's really been kind of ad hoc, scratch my itch development. Everybody has something they're working on. They go and either add a driver for their scope or write a decode for the protocol they're working on today or something like that. And so I would really like to be able to find some contributors, or time in my schedule, good luck on that, to do more work on just core stuff and all the boring, non-sexy things that make a tool useful. So, for example, there's a couple of little annoying bugs, like the red and blue channels on the eye pattern are swapped on Windows right now. So the colors all look wrong compared to on other platforms. There's a few little tidbits like time-based and trigger configuration aren't persisted in save files. If your locale uses commas as a decimal separator instead of a period, the preferences file doesn't parse correctly. Little things like that nobody's bothered to put in the effort to fix. And so a lot of these little things have to get taken care of. I would like to hit a 0.1 release this summer to fall, and kind of, we haven't made an official goals for that release yet, but as a minimum, I want to have some kind of a packaged installation so that you can just go download a binary and install it. Right now, you have to pull everything from GitHub and grab a couple of different submodules and third-party dependencies, and it's a bit of a pain to set up. And so if we had just a binary distribution that engineers who aren't necessarily software developers could just go and use, improving the state of documentation, at least making sure all the basic features are documented, even if not all the protocol decodes and stuff are documented, at least having documentation for all the basic user interface features, being reasonably sure that there's no known showstopper crashes. The file format is at least stable enough that we know files created with this version will continue to work in future versions. And even already, just because I have so much test data, I've tried to maintain compatibility with older version save files, but making a little bit of a more formal commitment to that is kind of what I would expect.
You don't end up with a different
release.
API every release.
So file format stability, yes. The APIs are not at all stable. The 0.x series APIs will be changing. New functions will be added. A driver made with an older version may not compile with a new version because there might be a pure virtual function you don't implement yet because it didn't exist in the previous release, and so on. So the 0.x series, one of the goals is to kind of pin down that API stability more and get at the point that by the time I make a 1.0 release, there will be some semblance of API stability where at least, I'm not going to be targeting binary compatibility anytime soon, but as a minimum, I want to ensure that a source code compatibility for a driver written for an older instrument will still build on newer versions. At least for, the 1.x version series. Maybe 2.0 will start making some breaking changes. But yeah, 1.0 is not going to happen this year for sure. I'm hoping to get 0.1 out this year, but it also really depends on how much support we can get from the community and manufacturers, because a year ago, glscopeclient, a year and a half ago more like, I think one person other than me had tried to compile it, and the code still had hard-coded references to files on my development machine, and it was just totally not in a usable state. And it's matured massively. We've picked up, I think we're up to like 10 or 15 people have at least contributed some code whatsoever, and we've got a couple somewhat active contributors now. So if it continues picking up steam like this, who knows where it's going to be in another year.
Great. So just as a final thing, do you want to say a few words on your offer to the community about helping debug, like, because we've just heard like it can be very expensive. You need expensive tools. You need expensive software sometimes. And I know that you've very generously in the past helped people out with open source hardware projects if they need it.
Yeah. So basically, the idea is Anti-Kernel Labs is legally a business. I need to be able to, for example, pay taxes on my boards that I sell and so on. So I had to get a business license and register it as such and so on. My goal is not to make it something I can live on anytime soon. It's really my playground and something to work on in my spare time and so on. And so ultimately kind of my goal is for it to run roughly at break even. I would like to be able to sell boards and potentially consulting or support services here and there in order to subsidize development of future projects and use that also to subsidize the cost of providing services to the community. Because, again, I recognize that I have substantial budgets that the average hobbyist is not going to be able to afford. I mean, just looking at pictures I've tweeted in my lab, you can probably get an idea of how much I spend on it in a year, and it's definitely well into the 5 digits. And so that gives me a budget and capabilities that, again, are not necessarily going to be on par with a large corporation, but certainly beyond the means of the average private individual. And so I do try to be aware of that and give back to the community as much as I can and provide either pro bono or heavily discounted services for example, if somebody gives me Gerbers, throwing that in the queue to do an EM simulation on is basically just a matter of importing and throwing a couple of ports on it, maybe cropping out the region of interest or something. It doesn't really take that much of my time. And if I'm away at my day job anyway, I'm not sitting at my desk running simulations anyway. So if I don't have something in the queue, it doesn't really cost me anything to go take that software I've already paid for and use it more heavily. And then I don't think anybody's taken advantage of this yet, but I am also open to doing hands-on either testing, characterization, measurements, failure analysis type stuff. I've done a little bit of like board cross sections for applied ion systems. For example, I did some cross sections of a failed capacitor for him, and so on. And really, I kind of consider it a communist pricing model. So pay what you can afford. I'll give you what I can. And
you mentioned that when things open up a bit in terms of the pandemic situation, then you might be looking at doing some face-to-face training as well.
Yes. So actually, I'll just pick the camera up for a second and look off that way. I've got a whole classroom space with whiteboards, and there's no projector yet, but I've got the screen for where a projector is going to go and so on in here with seating for up to 4 or 5 students. And so I do plan on offering in-person trainings. My lab obviously will also be included as part of that. I haven't worked out exact details. And again, I'm not trying to make a living off of this. There are certain things where there's expensive consumables or components, something like that, that I'll at least, I'll need to charge return shipping if you send a board to me and you want it back, or, cost of components and swapping parts or something like that. But for the most part, I'm trying to subsidize the cost of doing this out of sales of boards and so on, and kind of get the point that it's running at a net neutral. I am looking at running in-house trainings and practice sessions, and my lab certainly massively beats the teaching labs when I was in school.
So how should people get in contact with you if they want to find out anything more about your tools or glscopeclient, or about training, or about your offering to the community?
Following my Twitter is probably a good start. Antikernel.net is the website for the lab. Sales@antikernel.net is the email address to contact stuff through there. That also will link to if you want to buy the probes or something along those lines. And again, I don't really have definite either time frames or plans as far as trainings go, and it'll really kind of be if a couple of people in the area reach out to me and are all interested in learning advanced soldering, I'll go throw something together some weekend.
Great. Okay, well, thanks so much for your time, Andrew. It's been really good talking to you. And thanks for sharing all your great and deep technical knowledge on all of this high-speed signal integrity and measurement systems. It's been great.
Thank you.